Welcome back. In the next part of this lecture, we'll be talking about establishing trig identities. So now we are going to take what we already know, our older identities, and use them to show that something else is an identity. So we'll have a statement, an equation where there's a left side and a right side, and we want to show that it's an identity. In other words, we want to show that the left side is always equal to the right side. So how do we do this? Well, we'll start with one side of the equation, and usually it's the more complicated looking side, or the one where I can see that there's something that I can do with it. And then I'm going to modify that side of the equation using identities that I've already established until I can show that that one side it can be transformed into the other side. That's basically it. We're going to pick one side and rewrite it and transform it using identities until we can show that it's equivalent to the other side of the equation. We do have to be careful here. We're not going to start out with saying that the left side and the right side are equal and then moving things around, because that's assuming that the left side and the right side are equal to each other. So what we're going to be doing now, whenever we're doing establishing identities, is always working with one side at a time. So, for example, with this first problem, this would be incorrect if I decided to start modifying this equation by, let's say, I felt like multiplying both sides by cosine squared to move things over. Well, unfortunately, what we're trying to show is that the left side and the right side are equal to each other. We don't know that they're equal to each other yet. And so, how do you know that if you move cosine squared over here that the left side and the right side will be equal? That's what we're trying to show, which means we can't use that yet. So instead, what we're going to do is look at one side on its own, show that can I transform that one side into the other side. So we're not going to treat this as something where we're trying to solve for theta. We're not moving things from one side to the other. We're always trying to see, can I transform one side of the equation into the other? And so the choice that I'm going to make here is to start with my left side. And that's because, number one, it's the most complicated looking side, but already I can see one thing that I can do. Namely, I've got that sine of negative theta, and I know that I have that even odd property of my trig functions that I can call upon. So that's what I'm going to do for my first move. I'm going to start off by saying that sine of negative theta, we know that that is the same thing as negative sine theta. All right, so we're getting part of the way there. So what do we have next? Well, again, you've got multiple options as to what you might consider doing. I'm going to think about this, that we've got cotangent that I could write in terms of cosines and sines. So that's what I'm going to do next. I'm going to actually rewrite this and say, well, we've got sine theta. We have that cotangent squared theta, which is cosine squared theta over sine squared theta. And then the whole thing, I've got cosine squared theta in the denominator. And I could clean that up a little bit. You can see that the sine and the one of the sines will cancel. So I'm left with negative cosine squared over sine. And then the whole thing is over cosine squared theta. Now, of course, if it's all over cosine squared theta, that's like it's all over cosine squared theta over 1, which is the same thing as multiplying the whole thing by 1 over cosine squared theta. So actually, that line that I had previously could be rewritten as negative cosine squared theta over sine theta times 1 over cosine squared theta. And I can see now that the cosine squareds cancel very nicely, leaving me with just negative 1 over sine theta, which is the same thing as negative cosecant theta, which is my right side. So I've shown but the left side can be transformed into the right side. I started with the left side, and I applied identities one at a time, doing a little bit of algebra to simplify, and I showed that, yes, the left side could be rewritten as the right side. So that means that this is an identity. Anytime you see a negative cosecant theta, you could, if you felt like it, replace it with this expression, and it's equivalent. All right, let's do another one here. We've got some sine squareds, some cosine squareds. Whenever I'm thinking about what identities to use, I always ask myself, what do I see and what is it reminding me of? And I'm looking at this and I see sine squareds and cosine squareds, which is making me think very much of the Pythagorean identities. So I'm going to start with this. I'm going to begin with my left side here. I have 3 sine squared theta plus 4 cosine squared theta. And one thing that I know is that sine squared theta plus cosine squared theta is 1. So if I were to just take this for a minute and rewrite this as 3 sine squared theta and then the 4 cosine squared theta, I'll split that up as 3 cosine squareds plus 1 more. So nothing really fancy has happened here, but these two terms that I have, 3 sine squared theta plus 3 cos squared theta, that's the same thing as 3 times sine squared plus cos squared. And we know, courtesy of our Pythagorean identity, that sine squared plus cos squared is equal to 1. So this is really 3 times 1, which is just 3. And we can see that, yes, this is exactly the right side of our equation. So, yes, we've established that identity. Okay, let's do another one here. I'm going to start with the left side. This looks maybe more complicated than the other side. So, the left side I'll begin with. I've got 1 minus sine squared theta over 1 minus cos theta. And we've got a bunch of things that we could do if we felt like it. And the one that I'm thinking of doing here is that the sine squared theta, I'm thinking about our old friend, the Pythagorean identity. You know that sine squared plus cosine squared is equal to 1, which means that sine squared could be rewritten as 1 minus cosine squared. And that's my first move that I'm going to do here. I'm going to take that sine squared theta and rewrite it as 1 minus cosine squared theta. Now, if you're feeling kind of clever, you might notice at this point that you have a nice difference of squares here. 1 is a perfect square, and cosine squared is a perfect square. So actually, 1 minus cosine squared factors as 1 minus cosine theta times 1 plus cosine theta. And that's kind of convenient because the 1 minus thetas, or 1 minus cos thetas, now cancel out. We're left with 1 minus 1 plus cos theta. And if we just do our subtraction, we'll have 1 minus 1, which is gone, and we'll have negative cos theta left over, which that indeed is the right side. So we've shown left side is equal to right side, and yet again, that is, identity has been established. Okay, so this one, you can start again whichever side you'd like. I'm going to start with the left side here. It doesn't always have to be the left side. It could be the right side if you felt like it. It's whatever side looks more complicated, whatever thing you think might give you more options to do things. And here I can see one thing that I can do right away, which is that I know that secant is the reciprocal of cosine, so I can at least rewrite this as 1 over cosine minus cosine. And I could, if I wanted to, combine these together. I know that I kind of have to here because the left side, you can see that there's two terms, but on the right side of the equation, there's just that one term. So that means that if I'm trying to make the left side into the right side, then I really need to somehow turn this into one term, and I'll do that by making common denominators. At cosine theta, I'll multiply top and bottom by cosine theta, giving me cos squared over cos. And this has done some nice things for me here, namely that the numerator is something where I would have a lovely trig identity now. The numerator 1 minus cosine squared, if you're thinking about your Pythagorean identity, which hopefully you are, you'll know that 1 minus cosine squared x is the same thing as sine squared x. And we're almost finished because we now have sine squared over cosine, which is the same thing as sine times sine over cosine. And sine over cosine is the same thing as tangent. And there we go. We have it equal to the right side now. The right side of our equation was sine x times tangent x, and that's exactly what we've shown, that the left side, secant x minus cosine x, could be adjusted and modified so that it turns into the right side of the equation. Okay, left side of the equation is certainly the more complicated side to work with here. Of course, you could always start with the right side instead, but I think this has probably got more options available to us for what we can do. And I'm thinking right away my best move here is that since tangent and cotangent could be both written in terms of sines and cosines, that I'll probably be happiest if I start with that approach. So I'm looking at tangent theta minus cotangent theta over tangent theta plus cotangent theta. And I know tangent could be rewritten as sine divided by cosine. And cotangent could be written as cosine divided by sine. And this is sort of a fun flash from the past because if you're thinking back to the very beginning of the course, we began by doing things where we had complex fractions, fractions inside of fractions that we needed to simplify. And the plan that we had there was look at all the denominators that you have and think of what the common denominator would be for all of those fractions and multiply top and bottom by that common denominator. The common denominator would be sine theta cos theta. So that's what I'm going to do. I'm going to multiply top and bottom of this expression by sine theta cos theta. And so in the first term, sine theta cos theta, when I multiply it by that common denominator, the coses will cancel, leaving me with just sine times sine. So I'll have sine squared. In the second expression, the sines will cancel, leaving me with cosine times cosine, or cosine squared. And then I can say similar things about the bottom. In the bottom, the cosines would cancel, leaving me with sine times sine, or sine squared. And the sines would cancel, leaving me with cosine times cosine, or cosine squared. There we go. I just noticed that I'd had the wrong sign there. Sorry about that. So my original expression that I had, tangent minus cotangent over tangent plus cotangent, I turn them into sines and cosines. I've simplified that complex fraction so that now I have this. I have sine square minus cos square over sine square plus cos square. And I know that sine squared plus cos squared is equal to 1. So I have sine squared theta plus cos squared theta over 1, which of course that is just the same thing as what you have on the right side of your equation. That is just sine squared theta minus cosine squared theta. So we had originally tangent minus cotangent over tangent plus cotangent, and we've shown that that can be simplified into sine squared minus cosine squared. Let's do another one here. I'm thinking again about maybe making the left side my first approach, because I see I've got two fractions. I can certainly make common denominators and combine them together. And that seems to be a good move because the right side of the equation, there's only one term. So that's kind of why I'm thinking I should think about starting with the left side and combining them together. So for the left side of the equation, 1 minus sine u in the bottom, and 1 over 1 plus sine u. So for my common denominator, it would be 1 minus sine u times 1 plus sine u. So I would have 1 plus sine u as the numerator for the first fraction, and 1 minus sine u as the numerator for the second fraction. And I don't think I have enough room to write that all, but of course that's fine because these would be two fractions with the same denominator, so of course I'd be able to combine them and make them into one big fraction. Now, a lot of things are going to clean up very nicely here. In the numerator, the sine u, the 1 minus and the 1 plus, the signs cancel each other out, leaving me with just 2 in the numerator. And in the denominator, I have 1 minus sine times 1 plus sine. That gives me that lovely difference of squares, 1 minus sine squared u. So we're actually almost there, because if you're looking at this, 1 minus sine squared, hopefully you're thinking about your Pythagorean identity. If you had cos squared plus sine squared equal to 1, then 1 minus sine squared could be rewritten as cosine squared. So I'll say that what we have here is 2 over cosine squared u. And of course, remember that 1 over cosine is the same thing as secant, so 2 over cosine squared should be 2 secant squared. And there we go, that is exactly the right side of our equation. So the identity has been shown. Left side and right side, yes, they are equal to each other.